today I'm going to talk a little bit about adapting to a changing climate. What I'd like to do is really focus in on how we can manage pastures to increase drought tolerance in our pastures. Before I get started, I don't want to disappoint Perry or anybody else, but there is no silver bullet. You know, we talk a lot about genetics, you know, looking at crop genetics to increase drought tolerance. In the corn and the soybean, people who have a lot of money have been working on this with fervor. And in the progress that they've made has been pretty minimal, I would say. You know, 9% yield and increase during a drought period. It's significant, but it's not a silver bullet. And so there is no silver bullet for the drought problem. But what we can do is we can think about how we manage our pastures, and then by improving our management techniques, we can increase the drought tolerance in our grazing systems, especially to short-term drought stress. Since we're talking about adapting to a changing climate, I thought it'd be good to throw just a couple slides in at the beginning to look at what's happening in the climate. And this is from the National Climatic Data Center. And this shows a cyclic pattern in carbon dioxide levels in the Earth's atmosphere. So what I want to point out with this is that the carbon dioxide concentration in the atmosphere is cyclic. And we see it goes up and down over the last 650,000 years. But the point I want to make is that when we get closer to where we are today, we've never exceeded 300 parts per million carbon dioxide concentrations in the atmosphere, but we did in the last 50 years. And so there's something going on there, and it's probably because of the Industrial Revolution and releasing large amounts of carbon dioxide from fossil fuels into the air. This is the impact that we've seen on temperature. So we're seeing a rising temperature, and it doesn't look like a lot, maybe 1.2 degrees Celsius, but that's a lot in the global realm. So we're seeing an increasing temperature in the atmosphere. This was a paper that I came across getting ready for this talk, and this is a map of drought. It's the mean difference in number of drought months, and so what it's doing is it's comparing the number of drought months, so the average for the last century, and then comparing that to the prediction for the first half of this next century. And what they found is that we're going to have an increased number of drought months, but it's not going to be the same across the whole country. Where it's red, they're going to have significantly more drought in this area of the country. So as we move from the southwest to the southeast. But what's interesting, in the northeast and the upper Midwest, and even in the Midwest, we're seeing an equal number of drought months, or maybe even less, as we move forward. So I thought that was a pretty interesting slide. Now, how much faith do you put in this? We can't get the weather right 3 days out, let alone 50 years out. So I don't know exactly how much faith to put in this. But these kind of predictions are important because it shows that our climate is changing. And our climate is changing all the time. And what we really need to focus on is building robust grazing systems that can handle these kinds of variations from year to year. So what I want to talk a little bit about today is forage plant growth, and I think this is an absolutely essential topic for people to understand. We don't talk enough about forage plant growth at these type of meetings, and there's reasons why, but one of them is it's not real easy to talk about, and the second reason is it's not real easy for people to understand. So I hope I can do a good job in communicating some basic principles of forage plant growth to you today, because they're so important to understand. Once you understand those, you really start to understand how to manage that pasture under grazing. So today I'm going to talk about physiology. Don't get scared. That's just a fancy word for what's going on inside that plant. And then we'll talk a little bit about the morphology of the plant, another fancy word for the physical structure of that plant. How's it grow? Does it stand up? Does it grow in a clump? Does it spread out? And then how these two things to interact to determine how we should be managing that plant under grazing. If you understand those basic principles, then you can look at a plant and really understand how to manage that plant under grazing. I always like to start out with what we commonly think is the smallest part of the plant, and that's the plant cell. But even within the plant cell, we have smaller parts called organelles. And they're all held within this cell wall. And these organelles have special functions. And we're not going to talk about all of them today. We're going to talk just about a few. The chloroplast and the mitochondria and the vacuole are three that we're going to talk about today. The vacuole in the plant is kind of like, we can kind of think of it as a big sac inside that plant. And that vacuole has several important roles. But probably the most important role is that it maintains turgor in the plant. And what turgor is it keeps that plant rigid and upright. So if we think of this as our cell wall, and cell walls really aren't rigid like this plastic is. They're kind of semi-rigid, maybe like a canvas bag. But if we think of this as our cell, what the vacuole does is it's inside the plant. It's kind of like this balloon. But instead of being filled with air, it's filled with water. The way that the plant remains rigid or upright, or what we call has turgor pressure in that plant, is that vacuole blows up with water, and it pushes out against the sides of that cell. And when it does that, that plant remains rigid. When we undergo a drought stress, what happens is we don't have enough water to keep that vacuole inflated. So as that vacuole deflates, the plant wilts. And that's one of the primary roles of the vacuole within the plant. And we'll talk more about how a plant responds to drought as we get into this presentation today. The second organelle that I just wanted to mention briefly was the chloroplast. That contains all the machinery for photosynthesis. And we're going to talk about photosynthesis in the next couple of slides. And the last one is the mitochondria. The mitochondria is also known as the powerhouse of the cell. So it takes sugars and carbohydrates that we make during photosynthesis and breaks them down to release energy in a controlled manner from those that the plant can use for growth and persistence. Photosynthesis is, and I know it sounds like you're going backwards into your high school biology class, and you are a little bit, but I hope it's not too bad. But photosynthesis is important. It's the most important biochemical process on Earth. And it's the process by which light energy from the sun is converted into chemical energy that we can use and that plants can use. And what we're doing is taking carbon dioxide from the air, water from the soil, and we're converting it into sugars in the plant, in oxygen. It's not quite this simple, but this is the main gist of the process. And all this takes place in the chloroplast of the cell. That's that organelle within the cell that has the machinery to carry out photosynthesis. And the whole process is driven by light energy from the sun. When we look at our grasses, we have two major photosynthetic pathways in our grasses. We have what we call our C3 pathway. We find that in our cool season grasses. It's better adapted to carrying out photosynthesis at cooler temperatures. So we'll have maximum photosynthesis in a cool season grass when the leaf blade temperature is around 70 degrees Fahrenheit. So that makes our cool season grasses well adapted to growing in the spring and the fall, but not so well adapted to growing during the summer months because growth becomes temperature limited. Even if we have adequate water in the summer months, photosynthesis becomes very inefficient in C3 species at higher temperatures. Now, in contrast, our warm season grasses have the C4 photosynthetic pathway, and we think that our warm season grasses evolved from our cool season grasses to get around this problem of having inefficient photosynthesis at higher temperatures. So we'll have peak photosynthesis in a warm season grass at a leaf temperature of around 90 degrees Fahrenheit. That's important to remember because if we're in the summer and temperatures are hot, and we get a little bit of rain or we have a little bit of irrigation water, we need to use that on a C4 plant because they're much more efficient at converting that rain into dry matter because they're more efficient at carrying out photosynthesis. In fact, we'll fix about twice as much dry matter, produce about twice as much dry matter with a warm season grass per unit of water used in the summer months compared to a cool season grass. I know some of you probably cringed when I showed that chemical formula for photosynthesis, so I've got a kind of a cartoon model too, but it gets the same point across. We can kind of think of the plant leaf as the photosynthetic factory. And then, like any factory, we need raw materials to produce a product. And the product we produce in the photosynthetic factory are sugars and carbohydrates. So the raw materials that we need are sunlight, water, nutrients, and carbon dioxide. They move into the factory, we produce our product, sugars, and then they can go two places. They can go to the warehouse to be stored up in the plant, or they can go to the consumer outlet where they're used for growth and maintenance of that plant. And the question always is what determines where they go? Well, in a plant, what always gets first billing is growth and maintenance. Only once do we have a large enough photosynthetic factory that we're meeting the requirements for growth and maintenance of that plant does the extra sugars and carbohydrates get shifted into the warehouse where it's stored up for later use. This warehouse is really important in a plant because it's taking energy and it's storing that energy in the plant, and that energy can be used for growth after a drought stress, it can be used for growth after a plant overwinters, it can be used to maintain it during some kind of a stress period. And so having that warehouse as full as we can keep it is really important. And that's really what controlled grazing and rotational stocking is all about. It's resting those pastures, letting them build that photosynthetic factory back up after a grazing event, and store those carbohydrates in that warehouse so that when we do get under stress conditions, that we've got a full warehouse and lots of energy for that plant to use to persist through those conditions and adjust to those conditions. And we're going to talk about that in much greater detail in a little bit. Okay, let's talk about plant morphology. And remember, that's just a fancy name for the physical structure of the plant. And our grasses, we kind of have two types. We have a bunch-type grass, which kind of grows in clumps. We can think of a bunch-type grass as orchard grass or tall fescue. And I know when we look at a field, it looks like one solid stand, but if you really get in there and look, as the field thins out, we'll actually have bunches of grasses in there. They tend to have more upright growth than our sod formers. Our sod formers are things like Kentucky bluegrass and Bermuda grass that grows with the structures called rhizomes and stolons, or modified stems, which spread out across the soil surface, and they actually form a very dense sod. And just by looking at a grass and looking at its morphology, we can tell a lot about how it needs to be managed. A grass that's like a sod former that has a lot of leaves close to the soil surface and stores a lot of its energy in these stolons and rhizomes, it's much more tolerant to close and frequent grazing than a bunch grass, which has upright growth. So just by looking at a grass, if you understand a little bit about morphology, you can tell a little bit about how we should be managing that grass under grazing conditions. These are some structures of grasses and legumes. And when we look at the root system, generally speaking, for our legumes like alfalfa and red clover, we tend to have a taproot structure, so that's one primary root going down into the soil. And then for grasses, we have a fibrous root system. Normally in our cool season grasses, about 90% of those roots are going to be near the top of the soil. So that makes those plants very efficient at harvesting nutrients applied to the soil and things close to the soil surface in rainfall as it comes down. But as that soil dries out in the drought stress, when the top 8 to 10 inches of soil gets dry, grasses go under a significant drought stress. In contrast, something that has a deeper taproot system like alfalfa would have increased resistance to drought because it can go deeper into the soil to find moisture. The other structures I want to point out are these modified stems. And these are called rhizomes or stolons. And we find these in sod-forming forage species. And they have several important roles. They allow these plants to spread out and form a nice dense sod. And a stolon is above the soil and the rhizome is just below the soil surface. They also have an important function in that they store carbohydrates for those plants. And they're safely below the grazing height. And that's what makes sod formers very tolerant to close and frequent grazing. So here we have a pretty good defoliation event going on here. This is actually a horse, as most of you realize. And this is in southeastern Virginia. This was the tall fescue pasture. But what happened over time, horses are notorious spot grazers. So these horses came back to the same spots and they grazed the tall fescue. Every time we'll start to regrow, they will graze it over and over and over again. And finally, they grazed the fescue out. And what came in was a naturalized Bermuda grass that's very tolerant to close and frequent grazing. And so that's what this horse is actually grazing. So the question is when we have a grazing event in our pasture, if we have water and we have plentiful nutrients for that pasture to regrow, what's that plant need to regrow after it's been grazed off? Water. If we've got enough water and we've got enough fertilizer, what's it need to regrow? Energy, just like everything. whether we turn the lights on or whether we drive our car, we need energy, and plant needs energy for growth and maintenance of that plant. And in our grass species, it comes from two places primarily. It comes from leaf area remaining after grazing, so that's that photosynthetic factory. The closer we graze it, the smaller the factory gets. If we leave a little bit more grazing height on our pasture, the larger the factory is, and the faster the recovery of that pasture is going to be. And I know Dave Barker and Mark Schultz have done some really good research at trying to quantify that point at which you get maximum dry matter accumulation in terms of how much residue to leave. But generally speaking, if we leave a little bit more, just a little bit more residual leaf area when we graze a pasture, our regrowth is going to be much quicker. The second place it comes from for a grass is stored carbohydrates. So if we have a warehouse that's full or that plant has good energy reserves, that regrowth is going to be much quicker. So non-structural carbohydrates in plants, and I apologize if I didn't point this out already, but when I have a CHO there, that's an abbreviation for carbohydrate. These stored substance, non-structural carbohydrates are stored substances in plants that provide energy for regrowth and persistence of that plant. And basically, there's lots of factors that can affect the carbohydrate status of the plant, but basically anything that affects photosynthesis is going to negatively impact carbohydrate storage in the plant. So if we graze that pasture off, if we have water deficit, if we have decreased levels of carbon dioxide, so anything that impacts the photosynthetic rate is going to impact carbohydrate accumulation in plants. And this is just another diagram, and it's showing a similar thing. Photosynthesis is taking place here. We've got sucrose, which is the sugar being produced, and it's the first place that always goes is for growth of the plant and for maintenance of the plant. That always gets first billing. Only after we're meeting this requirement of the plant does the extra get shifted into storage. Now, this diagram, I know it's kind of busy, and I'm going to point a couple things out, but this shows where carbohydrates are stored out in the plant. Do you think that's important where it stores them at? Probably, because I put the diagram up, but it is important because it's going to impact how we manage that plant under grazing. So, for example, we have orchard grass here. And orchard grass stores its carbohydrates in the stem base. So what do you think happens to an orchard grass plant when we go into, say it's a hayfield even. Say we go into a hayfield. I think one of the worst things that's happened to orchard grass stands is the invention of the disc mower, because we can just cut so close to the soil surface with a disc mower. And what happens when we cut that plant off really low, close to the soil surface? What are we removing? Stored energy, plus all its ability to capture sunlight, right? Because we remove all the leaves, and then we get down into the stem base where it's storing its energy out for regrowth. So how do you think that plant's going to respond to close and frequent grazing or close hay cutting? Not well. Yeah. Mark says it's choking, yeah. And so the point is that not that we can't use orchard grass in a grazing system or a haying system, but we have to manage it a little bit differently than we would a plant like Bermuda grass, which stores its energy in rhizomes and stolons that are very close to the soil surface. And that makes that plant more tolerant to close and frequent defoliation. So the point is not that one storage area is better than the other. It's just that we have to manage those plants a little bit differently so we leave that storage organ after we graze it or cut it for hay. This is an example of carbohydrate cycling, and I'd just like to point out these diagrams are from an old publication. It was published in the 1980s from Dr. Roy Blazer, and that was a man that was ahead of his time in terms of forage management. And he has a great set of diagrams in some of his publications. This is showing carbohydrate cycling in alfalfa, and what we have here is a defoliation event. What's an alfalfa field look like after you cut it for hay? Is there a lot of leaf area left? No, it's all stems. But that regrowth, energy for regrowth is coming from somewhere. And in the case of carbohydrate, it's 100%. In case of alfalfa, it's 100% dependent on stored carbohydrates for regrowth. So what happens? We have a defoliation event. the plant starts to regrow, and we see a dramatic decrease in non-structural carbohydrate concentration in the taproot of the plant, where it stores its carbohydrates at. And then all of a sudden, when we reach 6 to 8 inches tall, what happens? It starts to go back up again. Well, that plant has reached a size where the photosynthetic factory, or the leaf area, is large enough that it's making more sugars and carbohydrates than it needs for growth and maintenance of the plant. So the extras get shifted back into storage. And by the time we're ready to cut that alfalfa field again or graze it again in 28 or 30 days, we're back up to pre-cut levels. All forage plants have a similar carbohydrate cycle in them. It's most pronounced in alfalfa, and that's why it makes a nice example. But all have a similar carbohydrate cycle. And if you understand this and you understand the whole basis behind rotational stocking, we cut it or graze the plant, and then we give it time to rest and rebuild our carbohydrates back up before we graze that pasture again. What would happen if we came in here and we let this plant get 6 inches tall and it's just starting to rebuild its carbohydrates, and we cut it off again? You can see we decrease the carbohydrate levels even more. And if we do that several times, like we would find in a continuous stocking system, all of a sudden the carbohydrate or the energy reserves in that plant gets lower and lower and lower, and persistence of that plant is going to be lower. In regrowth, is going to be slower, and eventually you're going to graze that grass out. It doesn't happen by overgrazing at one time, but when you do it continuously, that's when it really impacts that plant. All right. So this is a nice diagram from Dr. Blazer's publication. This is a grass tiller here. And what I want to point out is that when this collar, this structure called the collar, is present, this leaf isn't going to grow anymore. So the question is what do we do with that leaf? We know that in a grass plant that most of the nutritive value for our animals are in that leaf of the plant. If it's not going to regrow, what do we do with it? Do we graze it off or do we keep it? Don't answer yet. I want to just pass some tillers out. And this is Virginia tall fescue, not Ohio tall fescue, but I think they'd be similar in both states. The what? I had it hidden in my computer bag. They were more concerned about my shaving cream. All right, what I want you to look at on this tiller is I want you to look at that leaf that's similar to that one on there that's cut off here. And I want you to tell me what color is that. Is that leaf brown or red or what? You just pass that down to your partners there. I usually bring more plants, but I couldn't get any more in my suitcase. So what do we do with that leaf? Once that collar showing that structure right at the junction of where the new leaf is coming out at, what do we do with that? Do we keep it or do we graze it off? There's no wrong answer. There's just one that's more right than the other one. What do you guys think? I got to leave it. Anybody want to graze it off? All right, I got one, graze it off. Good. Tell me what color that leaf is. Green. So if it's not growing anymore and it's still green, what do you think it's doing? It's still carrying out photosynthesis. And that's important to realize, because where do you think the energy, if it's not growing, where do you think that energy is going? Back down into the plant, and it helps the fuel regrowth of that new leaf coming out. This is important to understand, because that's why we want to leave some residual leaf area in pastures. Even though we could graze it off and there's nutrition in those leaves, by leaving that leaf, even if it's not going to regrow much, we're going to fuel the growth of that new leaf coming out. So the answer is that we probably should stop and not graze all the leaf area off. This is a nice diagram. I know it's complex and I'm going to explain it, but if you look at one diagram when you go home today, look at this one again, because this is important. If you understand this, you really understand rotational stocking. And so I divided this diagram in half with this blue line, and if you're looking at it, on the left-hand side is what I call a rotationally stocked pasture, and on the right is a continuously stocked pasture. And then we do, and in a rotationally stocked pasture, we rest our pasture and we allow it to have time to rebuild its carbohydrates. And when we do that, we have a high carbohydrate status in that pasture. In our continuously stocked pasture, every time that grass plant grows up, what happens? It gets nipped off again, because animals, they like vegetative stuff, and they don't know any better. So they nip that growth off. So we have a low carbohydrate status in that pasture. All right, so high here, low here. And then we do two other things. We either leave 2 inches of residual leaf area on this grass tiller, or we trim it all the way off, right down to the stem of the plant. And then we look at the regrowth of those plants. And what we found was that, or Dr. Blazer found, was that when we have a high carbohydrate status and we leave 2 inches of leaf area, we got 1 inch of regrowth, and we got 4 new tillers formed on that grass tiller. 4 new tillers. When we have the opposite, so low carbohydrate status and no leaf area, we got half as much regrowth, and we got fewer than half as many tillers formed. This is important because this really shows us that having a controlled grazing system is not only going to increase the productivity of that system by increasing growth, and people find that a 30% advantage in some cases or more to switching from a continuous to a rotational stocking system. And it also keeps our sod thick because we're forming more tillers. And what happens in a thin sod? When the sod thins out, what do we get? If there's a hole in a pasture, does the good Lord leave it bare? No, he puts a Band-Aid on it, and usually that Band-Aid is a weed. And so we come into that pasture, and what do we do about that weed? We spray it, right? And we got some great herbicides now, great pasture herbicides. But what do? They kill that weed, and then what's left? A hole in the pasture. What grows in a hole? A weed. And the point is that it can be an ugly cycle if we're basing our weed control program only on herbicides. I'm not saying herbicides can't be an important part of a weed control program, but it's got to be a complete and integrated weed control program that involves grazing management. This was an accidental demonstration, and this was a research plot, a clipping trial for tall fescue varieties, and it was at the Tidewater Research Station, which is in the southeastern part of Virginia, and on sandy soil, so not ideal fescue soil. And they were helping me maintain the trial by mowing around it, so I didn't have to clip as much when I came down to harvest the plots. And they did a really good job. They mowed it at about less than 2 inches every week. And during the summer months. And you can look at the effect that it had in the amount of residual leaf area compared to a 3 to 4 inch residual height that we just talked about on this tall fescue stand. So just raising that residual height a few inches can make a big difference on how much leaf area you leave on that pasture. How do you think this is going to weather a drought compared to this grass right here that has been rested and has some leaf area left? This is going to be much more productive. And this is kind of similar to what we would see in a continuous stocking system where they just kept it grazed down all the time. All right, we always talk about what happens above the soil, but we need to be thinking below the soil too. And we don't have as much good data on that as we do above the soil, because it's much easier to do a clipping trial and weigh forages above the soil than dig up roots and measure roots and so forth. But there was a good study. It was done in the 1950s, and just because it's old doesn't mean it's not good. This was a root growth stoppage study done by Kreider in the 1950s. What he found was that when you removed 50% of the shoots, that we stopped root growth. When we removed 90% of the shoots, so if we had a 10-inch stand and we grazed it back down to 1 inch, we stopped growth for 17 days, root growth for 17 days. When we had 3 clippings per week, so that would be a kind of a system where the animals would come back and just keep nipping that grass off every time it started to grow up enough for them to get a hold of it, root growth never resumed. And root growth did not stop when we removed 40% or less of the top of the plant. So this is kind of where that rule comes from, that we should take about half of what's above the soil and leave about half of what's above the soil. And that's a pretty good general rule. What we do to the top of the plant is going to impact what's below the ground. And that's really what I want you to understand. We don't think about that enough. But if we abuse the top of that plant, we're abusing what's below the ground. We got 3 root systems here. This is a root system from a continuously stocked, maybe a little bit overgrazed pasture. This is a rotationally stocked pasture, and then this is a laxly used pasture. And basically what you see is the root system is much smaller on that continuously stocked pasture. The point I want to make is that when we get into a grazing situation, which one of those plants, a drought situation, which one of those plants are going to be better adapted to that drought? Probably that middle one, that rotationally stocked pasture. And that's one of the first things that producers notice when they switch from a continuous to a rotational stocking system, that their pastures grow longer into a drought stress and they recover from that drought stress a lot faster. So this is your test for the day. Let me go up there real quick. I'm probably going to make a screeching sound. But look, if we take orchard grass, for example, and we got a pretty close grazing height below 2 inches, look what's below there. What's below that grazing height? Is there a lot of leaves left there? Where does it store its carbohydrates at? In the stem base, so we're getting down into the base of the stem. So how's orchard grass going to do under that close and frequent grazing? Not too well. Not too well. But then we go to something else like Bermuda grass. Remember, it stores all of its carbohydrates in the stolons and rhizomes, which are safely below the grazing height. And it's got a lot of leaf area underneath that, even underneath that 2-inch grazing height. And it's going to be much better adapted to close and frequent grazing than something like orchard grass. And the point is that we can use any of these species in a grazing system. We just have to change how we're managing those species to favor that species. One of the other things that we don't talk enough about is the impact that we can have with grazing management on the botanical composition of pastures. In this example is alfalfa orchard grass mixture. Now, changing the grazing height of this favors one plant or the other. If we have a low grazing height, we'll tend to favor the alfalfa in this mixture. If we have a high grazing height, then we tend to favor the grass in this mixture. And because we talked about how these forage plants grow and where their energy comes from regrowth, we can kind of understand this. A higher grazing height is going to leave more residual leaf area in that grass, and it's going to make it more competitive in that mixture. A lower grazing height is going to put that grass at a disadvantage and let the alfalfa dominate. And this happens not just for alfalfa orchard grass mixtures, but we can use this whole concept of grazing management to change botanical composition in our pasture. So say we had a mixture of white clover and tall fescue in your pasture, and you were starting to get too much tall fescue and not enough white clover. One thing that you can do is lower your grazing height a little bit, and that's going to favor the white clover in that mixture. I've got a neighbor back home who's a really good grass manager, a little bit too good of a grass manager. And he has a really hard problem keeping legumes in his pastures because he leaves a good residual when he grazes through his pastures. And that residual favors that grass plant in that mixture. If he wants to get more legume into that pasture, he can graze those pastures a little bit tighter and open that sod up a little bit and put that tall fescue at a disadvantage to let red and white clover come into his pasture. So the point I want to make is just by changing grazing management, we can affect what plants are dominant in our pastures. And we always talk about pastures like they're We always talk about pastures like they're monocultures, but really, when you look at a perennial pasture, it's not a monoculture. It's got a whole bunch of diversity within that pasture. It's got things that we planted and things that we didn't plant. It's got weedy forbs that animals actually eat, and weedy forbs that animals don't eat, and weedy grasses too. And they're all part of that pasture system. Let's change gears a little bit and talk a little bit about drought. And this is something that's part of our agricultural landscape. And in this analysis that they did in the 1970s, which was a really nice paper, it's available on Ed Rayburn's Forage website, looks at long-term records for drought in the northeastern United States. And what they found was that drought, a moderate drought, occurs about once every 5 years, and a severe drought once a decade. And I think that's probably about right. Maybe it's becoming a little bit more frequent. But the point is that drought is part of our agricultural landscape. And we always are going to have drought, and we always will have drought. Yet every time a drought comes, everybody acts like they've never seen one before. What in the world's going on? I've never seen this before. No, you have. And the point I want to make today is that we need to manage pastures for drought, not just as we get into a drought or after a drought, but always manage pastures for that next drought. And I'm a proponent of people sitting down and thinking about how they're going to manage their forage livestock system during a drought. I think that's really important. And you don't have to sit down and write up a 42-page document, but make a few notes, make some benchmarks, and think about what you're going to do as that next drought comes. It's much easier to enact a plan than have a knee-jerk reaction next time you have a drought. And if you have a plan, it's going to save you a lot of emotional and financial stress as you go through a drought period. I want to talk a little bit about water relations in plants and how plants react to drought. And everybody knows water is paramount in forage production. We've got to have water for plant growth, and it often limits plant growth. And it's not necessarily the total amount of rainfall we get in a year, but it's how that rainfall is distributed across the season. So we can get 10 inches less rain and still have a pretty good forage season if that rain is well distributed. So seasonal distribution as much as the total amount of rainfall. So when we think about a plant, and a plant's going through a drought stress, what's its ultimate objective? Is it to grow and produce forage for your animals to eat during that drought period? I've got bad news for you. The plant doesn't really care about your animals. But all the plant wants to do essentially is survive. And it's going to do that ultimately by maintaining the growing point of that plant. Now, when we talk about a plant undergoing moisture stress, we often make like it's a switch, like we turn a switch from well-watered to drought-stressed. And that's not exactly what happens in a plant. As a plant starts to undergo drought stress, things happen within that plant, and that plant kind of acclimates to that drought stress. One of the worst things we can do is, as that plant's trying to adjust to that drought stress, or we're in the midst of that drought stress, is to graze it off to the ground. And that commonly happens. People get into a situation where it's dry, and what do? They open every gate on the farm up and just let the animals go through and pick every green leaf blade off of that farm. That's a disaster waiting to happen, because those type of pastures that are abused like that during a drought are not going to recover well after that drought's over. So what happens in the plant is it starts to undergo this moisture stress. The first thing that happens is we get reduced shoot growth. So that's that plant material above the soil surface. That growth slows. And a couple things happen that's kind of interesting. Cell elongation stops before cell division. So this, and I'm not an artist, so don't make fun of my plant leaf, but this is my plant leaf. The way a plant leaf grows is that at the base of the leaf, we have a zone of cell division. So the cells divide. It makes more plant cells. And then the cells elongate, or they kind of blow up with water, and that pushes the growth of the leaf out. And what I'm telling you happens is that this zone slows down. This zone of elongation slows down before cell division. And you're saying, well, why do I care about that, right? Well, let me tell you why you care about that. Because we get a stockpile of plant cells down here. So it's still dividing, but they're not elongating. So we get a bunch of plant cells at the bottom of the plant, and they're just dying to elongate, but they don't have enough water. So if we can maintain this leaf intact during a moderate drought stress, and it doesn't completely senesce, a lot of times we'll get very fast growth and recovery of the pastures once water comes. And the reason why is because we have this stockpile of cells. We just add water and we get an explosion of growth. It's kind of like compensatory growth in a thin animal. So you bring a thin animal in, you put them on a good nutritional plane, and you get a very fast growth rate. And that's what can happen if we can maintain this leaf during a short-term drought stress. The second thing that happens is that we get increased root growth in a plant. And we'll talk about why that's important in a minute. But essentially that root growth is reaching down further into the soil to look for water. And then we get an accumulation of sugars and carbohydrates. So we just said that we had a reduced shoot growth in the plant, but photosynthesis is still going on, so that energy is being stored up in the form of sugars and carbohydrates. That's an important part of the acclimation process. It's providing an energy source for that grass plant to go through the drought stress and then have energy to come back after that drought stress is over. So keeping that warehouse full of carbohydrates in the plant is pretty important. And eventually we get reduced photosynthesis. Plants in different parts of the world approach this problem of drought differently. In our area, in the humid area of the world, we have what we call dehydration postponement. And it means just what the name says. The plant tries to keep itself from drying out. The first thing that often happens is rolling of the leaf blade. And if you ever drive through Ohio and go through the corn country, in a dry part of the year, those leaf blades can be rolled up pretty tight. And it does that for several reasons. It just doesn't do it for no reason. It does it because it reduces the leaf area exposed to the sun, and then it reduces transpiration losses from that plant or water moving out of that plant by rolling that leaf up. And as that leaf rolls up and is reducing that transpiration loss, it allows those stomata in the leaf to stay open. And I'm going to talk about that in a minute, but that's important for photosynthesis and cooling of the plant. The plant then tries to maintain water uptake by expanding its root system. We said that one of the responses of the plant was increased root growth, and it's looking for more water in the soil. And then something happens called osmotic adjustment. And this is pretty interesting, but what happens in the plant, remember we talked about this plant cell and we had the vacuole inside of it? And you remember that this is a well-watered plant here where that vacuole is blown up and keeping the plant rigid. It has good turgor pressure. And then we get under a drought stress and that shrinks because there's not enough water to keep that vacuole blown up. And that's when a plant wilts under a drought stress. So what osmotic adjustment is a concentration of solutes inside this vacuole. So the plant concentrates sugars and carbohydrates and other compounds inside this vacuole. And what that does is creates a gradient across that cell membrane. And everything in nature likes to be in equilibrium or the same on both sides. So by creating a concentration of solutes inside here, the draw for water is greater inside this vacuole. So the plant can draw those water inside that vacuole and blow back up. And this is not a permanent, but a temporary fix for that plant. It's called osmotic adjustment. So all these things happen as that plant acclimates to this drought stress. Eventually, we're going to get what we call stomatal control. And that's when these stomata, these holes in the leaf, close. And we often think of stomata as just being holes, but they're not. They're specialized holes, and they have specialized cells on them called guard cells. And the guard cells can change their shape, and those holes can open and close. So what happens eventually is the last thing that happens in this drought adjustment process is the stomata, the plant senses that we have so little water left that we're just going to have to close our stomata to conserve water. Several things happen. One of the important functions, there's two important functions of stomata. They allow for gas exchange for photosynthesis. So carbon dioxide moves into the plant leaf through these holes so that it can be fixed into sugars in photosynthesis, and oxygen moves out. The other important thing that stomata do in the leaf blade is they allow for cooling of the leaf. So we can kind of think of the leaf, water moves up through the roots, through the stem, and then out these holes in the leaf, and that cools the leaf blade. What happens when these stomata close in the last stages of this acclimation to a drought stress is that the leaf temperature increases significantly. So that reduces photosynthesis because it can't have gas exchange, and we increase leaf temperature. This is the beginning of the end for this leaf blade. And eventually that leaf senesces. And is that a good thing or a bad thing? Well, it's not great, but it's a survival mechanism for that plant. The plant's saying, I've got so little water left, I'm going to use what water I have to maintain my growing point. And I'm going to let go of this leaf blade and let it die. I don't have enough water to keep it anymore. So that reduces this leaf area and lets that plant concentrate what little moisture it has to maintain its growing point so that it can come back after that drought stress is over. All right, we can't predict and we can't prevent a drought from happening, but what we can do is manage for recovery. And there are several things I want to mention real quick here that I think are important parts of managing pastures for drought. And one is soil fertility. We don't always think of soil fertility when we talk about drought stress, but it's important. Nutrients are involved in water relations in the plant, most notably potassium. So having the right potassium fertility in your fields are important for that plant to acclimate to that drought stress. No rocket science here, just maintain your P and K levels in that medium plus range. We'd love to see you have them in the high and high minus range, but at the current fertilizer prices, it's tough to put a lot of extra inputs into a grazing system. So if we can just keep them in that medium range, then we'll be in pretty good shape. pH is important because it affects nutrient availability in the soil, and that's a whole other talk, but essentially, when we have the right pH, the nutrients are going to be the most plant available in the soil. And that pH for most pastures is going to be around 6 to 6.5. If we're getting into alfalfa, then we need to push it up towards 7. And the idea is that we maintain soil fertility so that plant is really ready to recover after. So it acclimates during the drought and it's really ready to grow after the rain comes. Talk a little bit about nitrogen fertilization and drought. And I know nobody in here would go out and put fertilizer on a pasture or hayland during a drought, but we want to make sure that we limit nitrogen applications to avoid nitrate concentrations in plants. And I think something that we need to talk more about as we move forward is building stronger nitrogen cycles in pastures. Commercial fertilizer, nitrogen is 70 cents or more a pound. And that's really becoming a stress on the whole system, that cost of input. So introducing and maintaining legumes and building the stronger nitrogen cycles in pastures is becoming more and more important. So we can introduce and maintain legumes in pastures. We can focus on using organic nitrogen sources like manures and litters. And when they make sense economically. And one thing I'll mention just real quick is that if you only need the nitrogen in a poultry litter, for example, sometimes it's not as good of a buy as you think. And then controlled grazing system is important in terms of building these stronger nutrient cycles in pastures because we're getting a more uniform distribution of dung and urine within that grazing system. One thing to think about is we often have our drought stresses in late summer, at least in Virginia. And as we're moving into fall, I think we need to be ready to stockpile. And do you all stockpile in Ohio? Yeah. So stockpiling is one of the best ways to feed cattle during the winter months. Much more economical than feeding hay. So being ready to apply that nitrogen as it looks like a front is coming through and we can get a little bit of rain on it is going to be important in terms of stockpiling. And the type of nitrogen matters for stockpiling. We've done some work that showed that ammonium nitrate is by far our best nitrogen sources for summer nitrogen applications. We don't get any volatilization like we can have with urea with ammonium nitrate. I think one thing that we don't have a lot of research on, but the turf guys do, is fall fertilization. And after we go through a stressful summer, a lot of times putting just a little bit of nitrogen on in November can really help build that plant up, stimulate some tillering of that plant, and get it ready to grow next spring. We're not going to get a tremendous amount of growth that fall from that 30 or 40 pounds of nitrogen, but we'll get that plant ready to grow that next spring. And the turf guys have been on to this for a long time. So controlled grazing, I think, is an important drought management strategy, and more important than a lot of people think. But what we're doing with the controlled grazing system is we're really preventing overgrazing of our pastures. And that's maintaining that healthy root system of that plant that's going to be able to respond to that rain when the rain finally comes. We want to maintain a positive carbohydrate status in that plant by resting our pastures, and that's all part of the controlled grazing system. And then we're managing residual leaf area. And residual leaf area has several. We talked about the importance in terms of photosynthesis, but the other important thing is that the residual leaf area is going to shade the crown of the plant, so that's going to limit temperature stress on the crown of the plant. It's also going to shade the soil surface, and when we shade the soil surface, we're going to reduce the amount of soil moisture loss when we have some residue or residual height on those pastures, rather than a pasture that's grazed down like a pool table. And then if we can maintain that leaf during this short-term drought stress, sometimes we can get compensatory growth after the water comes. So our drought management checklist: maintain soil fertility. We want that plant to be ready to grow after that drought stress is over. We want to allow the pastures to acclimate to the drought. So one of the worst things we can do is go in and graze a pasture off during a drought period. And I know people do that, but you're much better off to put some hay out and feed some hay in a sacrifice area. Rest our pastures between grazing events. That allows that carbohydrate status to stay high within that plant. And after the drought stress, manage that pasture to leave a little extra residual, let it rebuild its carbohydrates and strengthen its root system back up after that stress is over. Leave plenty of leaf area in that pasture. Remember, it shades the crown of the plant, it shades the soil, reduces soil moisture loss, and again, it's allowing that plant to adapt to that drought stress by building carbohydrates up. And then feed hay in a sacrifice area. I think this is a very important drought management practice. As we enter a drought, instead of opening all the gates and letting your animals roam around the farm and graze all your pastures down, put them in one pasture if you get through your rotation and you don't have good regrowth. Put them in a pasture, your weakest pasture, feed some hay, and just realize you're going to have to renovate that pasture after the drought's over. And your neighbors will make fun of you, but that's all right. They're like, look at that idiot. He's out there feeding hay when he's still got grass in his pastures. Well, you know what you're doing? You're saving your pastures. And after that drought's over, his pastures aren't going to regrow, but yours are. They're going to recover much more quickly. And avoid multiple stresses, I think, is the take-home message on our pastures. A lot of times we blame drought for killing our pastures, but really what it is accumulation of stresses. So we've got poor grazing management, we've got poor fertility, and then a drought comes along, and the drought is like the straw that breaks the camel's back. And the pasture dies, and then the drought gets all the blame. And really the blame needs to be laid on the poor management prior to the drought. In most cases, not all cases, but most cases, when we have a short-term or a moderate drought stress, most grasses are going to survive through that drought stress if they were well managed prior to that drought stress. And of course, it never hurts to ask the good Lord for a little bit of rain. All right, that's all I've got for this morning's presentation. Any questions? Yes, sir. In our work, ammonium sulfate was a close second to ammonium nitrate. And so that'd be a good choice to use for a summer fertilizer application. And we've done some work with nitrogen protection, looking at things like agrotane and Nutrisphere. I don't know if you all have Nutrisphere here, but it reduces the volatilization of urea products. And I haven't seen any real big benefits of those in my research, at least. And there's a certain cost associated with those too, nickel to a dime a pound of nitrogen to put those on. Any other questions? Thank you very much for your attention this morning.